Okay, let's start. We're doing optimization today. I believe this is 4.6. So this is one of the, again, one of the main uses of derivatives is to so-called optimize something. So in short, to optimize a situation means to make it as good as it can be. You want to create the optimum situation. And so the idea behind this, how we can use calculus to do optimization, there are many other ways, but calculus is one way to do optimization, is to pretty much try to formulate the optimum situation in terms of maximizing or minimizing something. You want to make something as large as possible or as small as possible. So, for example, if you're talking about profit, you want to maximize profit. You want to make as much money as possible. If you're talking about cost, you want to minimize costs. You want to pay as little as possible, and so on and so forth. So there are a lot of times when to make something as good as it possibly can be is equivalent to making something as large as possible or as small as possible. And that's where calculus comes in, because we can use calculus to identify maximum and minimum points. So the idea is to optimize something, we're really going to do it in such a way that if we can find a maximum or minimum point to get some desired result, we can use calculus to do that. There's another thing that's very important, and that is the idea of a constraint. Because in life you don't have infinite resources. Sometimes you need to, right? You're going to have limits. You're going to have restrictions. You're going to have constraints. You can't just do as much as you want, right? So you want the maximum profit, sure, but you don't have an infinite amount of workers making an infinite amount of products, selling to an infinite amount of people. You have like 10 employees, and they can only make so much, right? They're always going to be something that's kind of containing how much you can do, and this is called a constraint, some sort of restriction that is holding you back. And so optimization also takes that into account. It's making something as large or as small as possible, whichever one you need, but it does so within the context of a constraint, right? And basically, we can use calculus to set up this kind of situation whenever it's applicable. And just like with related rates, there are a standard sequence of steps by which you can solve any optimization problem in this class, and you pretty much go through the steps in this order, and that will ultimately allow you to solve such a problem. So one, as always, optimization problems are going to be, again, word problems, so reading the word problem is very important. One, you want to identify it as an optimization problem, and usually that would come with, the problem is going to ask you to maximize or minimize some situation within a certain constraint. Okay. Second, again, similar to related rates, you want to draw a diagram to describe the situation. This can help you come up with the equations necessary that you're going to want to set up. Three, the third thing is you're going to want to set up two equations. When it comes to optimization, there are two sets of equations that you need to set up. One equation is the constraint equation. This is going to be an equation that describes the restriction that you have, right? Whatever is limited, you need an equation to describe that thing. You're also going to have another equation called the objective equation. And that's the equation that describes the thing you want to make as large as possible or as small as possible. It's your objective to maximize or minimize that thing. And then the next step, because usually your optimization, your objective equation will have several variables, you can get around that problem by solving for one variable in your constraint and plugging it into your objective, which is the next step. This gives you the objective in one variable, and that brings us to the next step, which is to differentiate, right? So we're going to use calculus to find the maximum or minimum, and so we want to find the absolute max or min, which involves finding critical points, which we looked at how to find those last time. So technically, you want to find the absolute max or min. However, in practice, it's very rare that the endpoints will ever be a solution, so really, you're ultimately finding the local maxes and mins, because the endpoints will usually be some sort of extreme that doesn't make any sense. And we'll look at that when we're going through the problems. Step 6 is to answer the problem. So you're going to be asked for something very specific. You need to give that answer. Okay? That's kind of basically it. I think we can illustrate the problems nicely by just going through the examples. The first example is one that's very easy, and I think it illustrates the problem, the steps nicely. And then we'll do a few more examples to kind of see how we can apply this strategy in very different contexts. So the first one, it's actually very similar to a problem you've seen before. If you remember Javon's llama problem, right? When he's trying to build a fence in his backyard to contain all the llamas and he wanted to maximize the area. We didn't need calculus there because the function we came up with was a quadratic and we know how to maximize that. But in general, we don't have a vertex form for any random curve, so that's where the calculus comes in handy. So let's actually do this. Let's go through example 1 in the handout. First problem, first part is to read. We're going to read very carefully, make sure we understand the situation. So a farmer has 100 feet of fencing. He wishes to make a rectangular enclosure. If he wants the enclosure to encompass the maximum possible area so that he can plant the maximum number of crops, what should the dimensions of the enclosure be? So here you see he wants to maximize something. He wants to build a rectangle, but not just any rectangle. He wants to build the rectangle with the largest possible area. So this brings us to step 2, which is the diagram, and we're going to start to draw a diagram. And in this case, it's a rectangle that was described to us. The question asks for the dimensions, so it means that I don't know the dimensions in the beginning, so let's call the length x and the width y, just because. Right? So the goal is to really figure out x and y. What is the constraint in this problem? What do you think? Yeah?
Is it the 100 feet of fencing?
The 100 feet of fencing, right? So he doesn't have all the fencing in the world. He doesn't have an infinite amount of fencing. He has 100 feet of fencing. So the restriction is the amount of fencing that he has. Okay? So we have 100 feet of fencing. We want to create a rectangular enclosure that will have the maximum possible area. And you can realize that there are many ways you can actually do this, right? You could do this side is 20, that side is 20, that side is 30, that side is 30. You could do 25 by 25 by 25 by 25. You could do 10 by 10 by 40 by 40. There are many options. The goal is you need to find the best one. Which one would give you the maximum area? In this case here, the area is 600, right? In this case here, your area is 400, which is actually worse. 600 would be a lot better. In this case here, your area is what? It's 25, 10, 25.
625.
Huh? 25. Okay. So it looks like out of these configurations, this one is the best, but is it the best in general? That's what we want to actually figure out. What's the best possible way to construct a rectangle where the amount of fencing used is 100? Okay. So that leads us to the optimization problem. So let's actually go through it in the standard way. In this third step, we're going to figure out these equations. We're going to figure out the constraint equation. That's the equation that describes the restriction that you have, and the objective equation. So there are two equations that we need. This one here describes restriction. It'll usually be the, and pretty much in this class, it'll always be it'll usually be the guy with the given value. So here, there is something that they actually tell us what the value of it is. There's 100 feet of fencing. This is how much fencing you have, 100, right? So they gave you the value of the fencing. That's a constraint. You don't have unlimited fencing. You have 100 feet to get the job done, okay? So that would be usually the guy with the given value is going to be your constraint, but it's whatever is restricting you. So in this case, what is the restriction?
100.
Yeah. Right, so we need to come up with an equation that describes that. The feet of fencing is really the perimeter around this rectangle. So the perimeter equation is going to be the constraint equation here. We know that the perimeter has to be 100. This allows us to come up with an equation based on this diagram that describes the restriction. I can also say x plus y equals 50. And this is my constraint equation. This is an equation that describes the constraints that are on my x and y. The sum of x and y must be 50. What about the objective? What is it that we want to do? Yeah?
We want the largest area, so
We want to maximize area, which means the equation that describes area is going to be our objective equation. And based on this diagram, what would be that equation? Yeah? X times y. Length times width. Now ultimately we want to maximize this, which means we're going to find derivatives and critical points and all that. But the problem is there are two variables here. We're not in Calc 3, we don't know how to do multivariable calculus yet. So we need to actually fix that. We need to get rid of one of these variables. And that's what brings in the need for step 4. So in step 4, you're going to plug the constraint into the objective. Now this accomplishes two things. For one, it allows your objective to be in one variable. So here, I know that x plus y equals 50. I can solve for one variable here. In general, it doesn't matter who you solve for, but you tend to solve for the guy that's going to make your life the easiest. In this case, though, everything's pretty symmetric, so I don't really see a difference between solving for x and y. So I solve for y arbitrarily, and what I do is now I plug that into the area. And that accomplishes two things. Now I know my area is a function of x, so there's only one variable to deal with. I can do calculus here. It also means that my constraint is now built into the function that I care about. So once I solve the equation with this function, the restriction is already a part of the solution that will arise. It's already inside of the solution. At this point, yes, technically this is a parabola that's inverted and I can find the vertex, but let's actually use the calculus here to get through to the end of the problem, so that we can see how to deal with it if it's not such a nice function. So this is our new objective function, which brings us to step 5. Now in step 5 is where the calculus is going to start to happen. We want to maximize. We want to maximize or minimize something. In this case, we want to maximize A. So we learned how to find maximum points. What we're going to do is we're going to find critical points. So this means we're going to find A prime equals 0 or undefined. This means, what's the derivative of this guy? I can write it as 50x minus x squared. So it's going to be 50 minus 2x equals 0. It's never undefined. So this would give me my x is 25. Now a couple considerations here. Usually if you're doing this process, and I don't have a little bit. Usually when you're doing this process, if you only get like one thing, that's going to be the answer. It's possible to get several things, so if we've got several x values, we needed to check which one actually maximizes this function. Usually if there's only one answer, that has to be the answer you want. But technically, you do want to test to make sure. So you would test with the first derivative test, just as we do normally. So here you have your A prime, here's your 25. Of course, the minimum possible length of x is 0, the maximum possible length of x is 100. So I just pick some random numbers over here. So let's say I pick a 1 and it's 26. Plug that into the derivative. If I plug in 1 here, that's just 50 minus 2, that's positive. That means it's increasing. Plug in 26 here, that will give me a negative number. So that's decreasing. So I know that this guy here is a maximum. So you can test it in principle, which is especially needed if you have several possible x values. You want to know which x value is the right one, you just do like a first derivative test. The other one is technically you want the absolute max and min, so you should consider the endpoints. But as I said, these will rarely be the answer, but it is something you should consider anyway. So the maximum amount of fencing that I could devote to the x is 100 because I have 100 feet of fencing. But so if x is equal to 100, that would actually be my y equals 0, and that means no enclosure. I can't create a rectangle if my width is 0. Right? Similarly, the other endpoint would be x equals 0. I can devote no length of fencing to the length, but that would again mean no enclosure. I wouldn't have a rectangle if it has 0 length. So the endpoints do not solve the equation here. So I have one x value to consider. It actually gives me what I want. There's no contest from the endpoints, so that's my guy. That's going to be the guy that maximizes the area. This means x equals 25 maximizes area. And that finally brings us to step 6. Right, so the point of step 5 is to figure out the values that will maximize or minimize the thing you care about. And now step 6 is to answer the question. So in this question, if you read it, which you should have, that was step 1, it asked for what dimensions should the enclosure be, which means you need to answer the dimensions, which means your answer to this question needs to be, you need to tell me the length and the width of this rectangular enclosure. These are the dimensions of the enclosure. So I know that the length by my diagram was x. I know that's 25 feet. The width was y, which is, I think was 50 minus x, which in this case is 25 feet as well. So this means we need a 25 foot by 25 foot enclosure. That's your answer. Now, one thing I want you to realize here is there are multiple things that you could ask for in the end. The question could ask you to say, what is the maximum area, right? In which case, we know that the area equation was 50x minus x squared. So if the question asks you, find the maximum area, what we wouldn't have done this. You would have just taken the x equals 25 and plug it in here and here, and that would be the answer. But they specifically asked for the dimensions. So the answer must be the dimensions, not something else, right? Also, if you stopped here and just told me the answer is x equals 25, you didn't answer the question, right? The question tells me the dimensions. So it's very important that you read the question and give what is asked. Any questions? Okay. Let's just do some more examples. Really get used to this. Let's see. Let's move on to. Do problem 2. Design an open rectangular box with square ends on the left and the right side, having a volume of 36 cubic inches that minimizes the amount of materials required for construction. I want to say here. So This is an optimization problem. I know it's an optimization problem because it has the word minimizes in it. So there's something I want to optimize, and in this case I want to minimize the amount of materials I use to create this box. It's an open rectangular box, and I know the volume. So step 1 would be to read. Step 2 would be to draw a diagram. So here I have an open box. How would I label this box? Huh?
The ends were square, right?
The ends were square.
So it'd be the same variable.
Right, so if I call that x, I'd also call this x because it's a square. They didn't give me any other information about the other side, so that I'll call it a different variable, y. Alright, so again, you don't want extra variables running around. You want to keep things very tight here. Yeah?
Sorry, did it say cubed, 36 inches cubed or squared?
For what? Where?
Well, the volume is 36 inches.
No, volume is in cubic units, that's correct.
Okay, so, sorry, can I explain why you got 2 x's?
It's because of the first part of the sentence. It says the box with square ends.
Oh.
On the left and right, it's a square. So the length and the width are the same on here. Brings us to 3. We need to talk about our constraint and our objective. The constraint is the restriction. What's the restriction here?
Volume of 36 cubic inches.
Volume. They told us the volume. The volume can't be what you want. It has to be 36. So the volume is 36 is the constraint. So the constraint here is volume. Which means, how can I describe that with an equation? What is the volume of this box? X squared times y. This is my constraint equation. Right? That equation has my restriction built into it. The volume has to be 36. What's the objective? It's to minimize something. What do we want to minimize?
Materials.
How do you do that? Surface area. Right? So here you want to minimize surface area. If you have a smaller area of materials, the cost will be, the amount will be smaller, the cost will be smaller and all that. So how would I find the area here? The surface area.
XY plus like 4xy plus 2x squared.
Well, we have 2x squared, right? And that's for the left and the right.
Yeah. Oh, but there's 3
Plus,
3xy?
right, there's no top. So there's 1, 2, and the bottom. So there's 3 other sides, and the area of this side is x times y, the area of the back, x times y, the area of the base, x times y.
Yeah.
So it's 3xy, and this is for the other 3 sides. Right, so there are 5 sides in total because the box is open. That's why it's important to read, right? So we know that 1, we'd label it very suggestively for a square. 2, there's no top, so this will affect your surface area equation. You have to read very carefully. So that is our objective equation. That is going to be the equation that we want to minimize, but it has 2 variables in it, x and y. That's a problem. So we move on to step 4. Where we're going to essentially plug the constraint into the objective. So as always, we have a choice of variables we can solve for. What do we want to solve for here? I'd solve for y. Again, it doesn't matter who you solve for technically, but if I solve for x, I would end up with square roots, radicals, and I just don't want to deal with that. So it seems easier to me to solve for y. And of course, if I'm dividing by x, I have to assume that x is not 0, which automatically means my endpoints are not even going to consider. Right? And say, well, I could devote zeros, a length of 0 inches to the side. No, 1, you wouldn't have a box. 2, it wouldn't make sense in this equation. So then what you do is now you plug that into the objective. So now I would have a equals 2x squared plus 3x times the y. We can simplify that a little bit. This plus that. So that's 2x squared plus 1/8 over x. So that's my new objective. That's the guy we can minimize. Brings us to step 5. Want to minimize a. Notice here, again, endpoints don't work, so I don't have to check the endpoints. So secondly, I'm going to find the critical points then. This is where a prime equals 0 or undefined. Undefined happens when x equals 0. This reject. I wouldn't have a box if x equals 0. Or the other possibility is the derivative is 0. The derivative of this is what?
4x plus minus 108x minus 2.
Right. So you can bring this up. 1 over x is x to the minus 1. Do the power rule. Get minus x to the minus 2. End up with this guy. Or in other words, you end up with 4x minus 108 over x squared equals 0. How do we solve for that for x? Solve the equation.
Can you bring the 108 over x squared to the right side? Like
Sure.
that?
And then what?
And then multiply by x squared.
Yep. And you
And
could even
divide by-
multiply x squared in the beginning. X squared times this, 4x cubed. X squared times this, is 108 equals 0. And so I have 4x cubed equals 108. And so I have x is basically the cube root of 108 divided by 4. Is that a nice number? Taking it all back to lecture 1, how to solve random equations. Well, 108 was 3 times 36. 36 is 4 times 9. So this is really 3 times 9.
It's 27.
So what is the cube root of times 9?
3.
So it's 3. So that was a nice number. Ugly. So x equals 3. Again, we only have one option to choose from here, so that's basically it. But you could do a test 3 and test it in a prime, put in like a 1, put in like a 4, realize it's like that and that. And so x equals 3 minimizes. Which brings us to step 6. Now the problem set to design a rectangular box open. So the idea is here again, design is talking about the dimensions. Tell us what length and width to construct the box, that's the design. And so, you know that x equals 3. This means that your y was, what did we solve for y? It was 36 over x squared. So that means means y equals 4, plus my x is 3, and so this means we need a 3 by 3 by 4 box. That would be the box that has 36 cubic inches of space in it, and it uses the least amount of materials. Any questions on that one? Let's do another example. The goal is, of course, to do so many of these, you have the steps memorized by the time you're done with your homework. So on the test, they won't be so bad. We're going to have a rectangular enclosure. So let's go to problem 4. A cylindrical can without a top is to be made to hold 8,000 pi cubic meters of liquid. It's a huge can. Find the dimensions of the can, which will minimize the amount of material needed to make the can. That is, minimize the surface area of the can. So we're going to make a cylindrical can. It needs to hold 8,000 pi cubic meters. But we want to minimize the amount of area, the amount of materials in the can. So in step 1, optimization, realize we want to minimize. 2, we're going to draw a diagram. It asks us for the dimensions. So with a cylinder, these are the dimensions. We have to, well, it said without a top, so there's no top really. So there's a bottom, that's your R. It's called the height of the cylinder, H. So if I tell you the radius and the height, you can design this can. No top. Okay, 3. Constraint and objective. What's constraint?
Volume is 8,000.
Volume is a constraint. The volume that this can hold is 8,000 pi units, cubic units. Volume of the can? Pi r squared h equals 8,000. You can divide both sides by pi. And I can solve for either variable here. Which one would you solve for?
H.
H, again, so that I don't have to deal with radicals. It doesn't really matter who you solve for, but there are things that can make your solving the problem harder or easier. So we have that as our constraint equation. What is the objective?
On the surface area.
Surface area. So what would be the surface area of this object? A can with no top, the radius is r, the height is h.
Pi r squared plus.
So we have pi r squared, that's the area of the base.
Plus, is it r times h? No, 2r? Is it divided?
Yeah?
It'd be like the circumference, like the circumference of
Oh,
this plate.
yeah.
Okay, so what would that be?
2 pi r h.
This is the area of the side. Yes, great. You get 2 extra bonus points on the next quiz. Can't say no one quiz.
Oh, really?
Okay, so the base is a circle. radius r. And to figure out the area of the side, yeah, you kind of slice it down vertically here and you unfold it, right? So you unfold. If you unfold this, ultimately you'll end up with a rectangle. The height of the rectangle we know is h, but this length here is really the circumference around the edge of the can, which is going to be 2 pi r, the circumference. So the area of that is 2 pi r h, the area of this one is pi r squared, and this is ultimately my constraint equation. So now we move on to the fourth step. Let's plug constraint into objective. So I know h is equal to 8,000 over r squared. This means I can go and I can plug in h into this equation. So my a would be pi r squared plus 2 pi r h. And cancel that. So I can write this as pi r squared plus 2 pi times 8,000 r to the minus 1. That's my constraint equation. No vertex form for that equation, so we have to use calculus. Move on to the fifth step, where we're going to want to minimize this. Again, just write this so I know that you're thinking about it. The endpoints actually don't work here. Right? The extreme values will be like the radius is 0, and it's not going to make sense. Or the height is 0, and then yes.
You should explain again like why the endpoints don't work and what they are.
The endpoints mean the maximum and minimum values of the radius and the variables used. Right? Theoretically, you can, like, let's not put any radius in it. That would minimize that would minimize stuff for sure. But it minimizes it in a way that doesn't make any sense. And if this is 0, and if your r is 0, then your h can possibly be 0 as well. The maximum would be, what, 8,000 or something like that. But neither of those would work, right? If you devote all of your materials to one dimension, you have nothing left for the other dimension, so the endpoints is not going to work. So now all we have to worry about now are the critical points on the interior. Because if I take the extreme values, it just doesn't make any sense in the physical context. And so I want to find a prime equals 0 or undefined. In the undefined case, it's going to be when r is 0 because I'm dividing by r. So again, I reject that because it doesn't make any sense for r equal to 0. So I'm really only solving for where the derivative is 0. And what's the derivative of this guy with respect to r?
2 pi r plus
Well,
minus
2 pi times 8,000
r
r
minus
to the minus 2, set that equal to 0. I can divide both sides by 2 pi. I can also multiply both sides by r squared. And so my r is going to be the cube root of 8,000, which is going to be 20. Again, you can test that, but it's the only possible answer. That has to be the guy. You realize that if I plug in 1 or if I plug in 21, I get that. And so r equals 20 minimizes. Now I move on to step 6. And step 6 asks for find the dimensions. So I need to say what the radius is. The radius is 20 inches or whatever. I mean, I don't really care. It's 20 meters, and the height. We had the height was 8,000 divided by r squared, I believe. So that's 8,000 divided by 20 squared, which is 8,000 over 400. That's also 20. So we need the radius equals 20 meters, the height equals 20 meters. That would create a can that has a volume of 8,000 pi cubic units, and the amount of material used will be as small as possible, the smallest possible amount. Do another example. Let's move on to example 5. A little bit more interesting. Let's see if we can get through this one. Same 6 steps, but of course, there's a little bit of variance to each of these, even though we're doing the same thing. So, the manager of a department store wants to build a 600 square foot rectangular enclosure in the store's parking lot to display some equipment. 3 sides of the enclosure will be built from redwood fencing at a cost of $14 per running foot. The 4th side will be built from cement blocks. The cost is $28 per running foot. Find the dimensions that will minimize the cost of the building materials. So here, very economically motivated, we want to spend the least amount of money in building this display enclosure. Again, it's rectangular, but 3 sides have one material and 1 side has the other material. So that makes things a little bit more interesting. Read the problem. 2. Come with a diagram for the problem. Again, we know it's a rectangle, but 1 side is different. Let me just highlight that side. On this side, we're going to build a wall. Build a wall. And then, now we can label this. So, it's going to be the best wall. It's going to be the wall that has the lowest cost, the most fantastic wall. So let's actually model the cost of this rectangular enclosure. What is the cost of this side? 14 times y. It's $14 per running foot, so y feet will cost 14y. Similarly, this side is going to be 14y. Again, this side is $14 per running foot, so the total cost here is 14x. What about this side? 28x. So on the wall side, it's $28 per running foot, so that's going to be the cost of that side. So that's my cost. So now we can start to set these equations up. So in the 3rd constraint equation, objective equation, what's the constraint here?
600 square feet.
600 square feet, that describes what? Area. Square unit, so it has to be an area. So I know the area that he can devote in his parking lot is 600. That's all the area he has in his parking lot to give to this display. Right? He doesn't want to use up any more area than that. But what is the area of this? It's what? Length times width equals 600. And again, I can kind of solve for anyone, but let's hold off on the solving first. Let's see what this guy's going to look like. It might influence my decision. So the objective here is we want to minimize cost. So we have to come up with a cost equation. Let's see the cost. And I realize the cost of each side, so I'm just going to add these all up. So it's 14x plus 28x plus 14y plus 14y. So that's, now things are getting serious, right? We're at 28y is 42, the answer to life, the universe and everything. And then, so here's it, it's not gonna, whatever, let's solve for y. Brings us to step 4. Plug constraint into objective. So if my y is equal to 600 over x, plug that into my cost equation, 42x plus 28 times 600 over x. Or I can think of that as 42x plus 28 times 600, x to the minus 1. Again, not something I have a general formula to find its maximum point, so I'm going to use calculus to find the critical points. My constraint is already built in, so finding the maximum of this will, the minimum of that will solve the problem. So we are going to step 5. We want to minimize C. So we're going to set C prime equal to 0. Technically or undefined, but that would mean that x is 0, so we're going to reject. Derivative is going to be 42 minus, because it's x to the minus 1, 28 times 600, x to the minus 2 equals 0. Multiply both sides by x squared. And so my x would be 28 times 600 over 42 and the square root. Is that a nice number? It's 20. Okay, that's a nice number. Of course, again, to be formal, when you plug these guys into the derivative, you're going to get that situation happening. And so x equals 20 minimizes. So this leads us to the final step 6. Find the dimensions that will minimize the cost. So I need to be talking about dimensions here. I know that the x side is 20. I also know that the y was 600 over x. So that means 600 over 20 is 30. So this means dimensions . So it's a 20 by 30 foot enclosure with one of the 20-foot sides is the brick side. And that's the best wall. It's the best wall. guys want to do another example? So we don't want to do any more optimization? Okay, let's move on to the next section. I'm kidding, get out of here. That's optimization. So the homework for this and all the curve sketching homeworks are due on Friday.
So that would be,
So the max and min stuff, the curve sketching stuff, and there were some sections where they asked you to do the first and second derivative test. I think. So it's like 4 point.
2 and 4.6.
Did you already give me 4.1?
Yeah.
Related rates.
Yeah.
Yeah. So 4.2 up to this. Up to
4.6.
4.6.
No,
Yeah.
I think you're 4.2. Depends what's on the.
Alright, well, show
Yeah.
During your office hours tomorrow,